So let's take stock of everything we've figured out so far. We've seen that if you assume a Poisson model for a series of IID observations, y1 through yn, then the maximum likelihood estimator for theta, the parameter of that Poisson distribution, is the sample mean, y bar. We've also seen that regardless of what the actual distribution of the data happens to be, that is to say, for any true distribution P naught, setting theta naught equal to the expectation of y yields the minimum Kullback-Leibler divergence from the true data generating process to a Poisson model. The best Poisson approximation, in other words, is to set theta equal to the mean. Now, we know from basic applications of the law of large numbers and the central limit theorem that the sample mean is, under very broad conditions, going to be consistent and an asymptotically normal estimator of the population mean as the sample size grows. So in this example, at the very least, we have found that the maximum likelihood estimator theta hat is a consistent estimator of the pseudo-true parameter value theta naught. That is to say, the value of theta that makes our model, f theta, do the best possible job of approximating the unknown true distribution in terms of minimizing Kullback-Leibler divergence. Just to emphasize this, we don't assume that this Poisson model is correct. The truth could be any other complicated sort of probability mass function that's not a Poisson. We nevertheless fit a Poisson, which seems perhaps like a crazy thing to do, and yet we do obtain something that is both interpretable and that has properties that are quite attractive, a kind of consistency for theta naught and also asymptotic normality. So is this just a coincidence, or is this a more general phenomenon of likelihood estimation? It turns out that it isn't a coincidence. And here is a general result for maximum likelihood estimation when our model may possibly be wrong. In other words, under misspecification. Suppose that we have an IID sequence of random vectors with some unknown true distribution P naught, and let theta hat denote the maximum likelihood estimator for theta under some possibly incorrect model f of y semicolon theta. Then, under some fairly mild conditions, it turns out that first, the maximum likelihood estimator theta hat is consistent for the pseudo-true parameter, theta naught. This is defined as the parameter value that minimizes the Kullback-Leibler divergence from the truth to our model over the parameter space big theta. Second, the maximum likelihood estimator theta hat is asymptotically normal. In other words, the square root of n times the difference between theta hat and theta naught converges in distribution to a normal random vector with mean vector equal to 0, and variance-covariance matrix, well, that's something complicated, but it's some kind of a sandwich, and the bread of the sandwich is J inverse, and the peanut butter is K. So what are these J and K matrices? Well, we define J to be -1 times the expected value of the second derivative matrix of the log likelihood with respect to the parameter vector theta evaluated at the pseudo-true parameter value theta naught. And we define K to be the variance of the derivative of the log likelihood with respect to theta evaluated at theta naught. So why should we care? Well, as the old saw has it, all models are false, but some models are useful. If we acknowledge that our models are incorrect, then we want to have some theory for maximum likelihood estimation that doesn't rely on the assumption that our models are true. And that's exactly what we now have. The previous slide gives us an interpretation of maximum likelihood estimation when we acknowledge that our models are only an approximation of reality. In this case, maximum likelihood estimation recovers the pseudo-true parameter theta naught. So it's consistent and asymptotically normal for this parameter. It also yields a way for us to calculate standard errors that's robust to the misspecification of our model. You can compare this to the way that when we do a linear regression, we don't necessarily need to assume homoscedasticity. We can just run the regression and then correct the standard errors after the fact for the possibility that, in fact, the variance of the errors is changing with x. Now, if indeed our model is correctly specified, the result in the previous slide reduces to a more familiar result. So here is a version of the result from 2 slides back with an extra assumption. Now we're going to assume that the model is actually correct. In other words, we're going to assume that P naught is equal to f of theta for some particular value of theta. An example would be we have some data that really did come from a Poisson distribution. We just don't know the value of theta. So in this case, maximum likelihood estimation is still consistent for the pseudo-true parameter. It's just that now the pseudo-true parameter value is the true parameter value. And we still have asymptotic normality, but what we now find is a much simpler expression for the asymptotic variance-covariance matrix. Previously, it was a sandwich, and the bread was J inverse. Now, it's just J inverse, where again, this matrix J is defined as -1 times the expected value of this second derivative matrix evaluated at theta naught. So why does this result follow from the previous one? Well, the answer is, if in fact the model is true, then the unique parameter that minimizes the Kullback-Leibler divergence is theta naught, the true parameter. We showed this in one of our earlier videos. When the model is correctly specified, you can make the Kullback-Leibler divergence be exactly equal to 0 simply by choosing the true parameter value. So that tells us why we're consistent for the true parameter value. Now the question is, where did we get this simplification of our sandwich, which formerly had bread and peanut butter being K, to now only have one piece of bread, the J inverse? Well, this comes from an important result called the information matrix equality. What the information matrix equality tells us is that, in fact, under correct specification, so that is to say, if our model is right, if our model is really the true data generating process, then the matrix K is equal to the matrix J. So in this case, you simply plug in a J for K, you'll have a J inverse times a J, which cancels and gives you an identity matrix. And that's where we obtain the simplification. To use these results in practice, of course, we need to have estimators of J and K. So on this slide, I show you consistent estimators for each of them. I also show you in the left column all the population objects, and on the right column all of the sample objects so that we can compare. Let's start at the top. The pseudo-true parameter value is the value that maximizes the expected log likelihood. The maximum likelihood estimator is the value that maximizes the sample analog of that expectation, namely the sample log likelihood. We have an asymptotic result, which says that the maximum likelihood estimator is consistent and asymptotically normal. This justifies the approximation theta hat is approximately normal with mean equal to the truth, and if we plug in an estimator of J and an estimator of K, they're both consistent, then dividing by n, which we need to do because, remember, the asymptotic result has a square root of n multiplying theta hat on the left-hand side, we obtain an approximation that we can use to actually carry out inference in real life. The only question that remains is, where are we going to get these estimates of J and K? Well, if you remember, J was defined as the negative of the expectation of this second derivative matrix evaluated at theta naught. It turns out, and if you're interested in knowing why this is true, you can take a look at the paper of Newey and McFadden. It's actually a handbook chapter from 1994. It turns out that the following is a consistent estimator. What do? we replace the expectation, which is a population average, with a sample mean. That's an average over the data we have. We calculate the second derivative matrix of the log likelihood, but because we don't know theta naught, we just plug in our estimator theta hat. We can do exactly the same sort of thing for k. Remember, k was defined to be the variance of this vector of derivatives with respect to theta of the log likelihood, again evaluated at the pseudo-true parameter value. So what do we do for k hat? Well, we replace with a sample analog, and again, we are plugging in here the maximum likelihood estimator, theta hat, instead of the true but unknown theta naught. So a few questions about the preceding slide. Whatever happened to the Kullback-Leibler divergence? Didn't we start off by saying, well, we'd like to try to minimize this approximation error, if you will, from using the model F to try to represent reality, P naught? Well, as we discussed in an earlier video, minimizing the Kullback-Leibler divergence is exactly the same thing as maximizing the expected log likelihood. So it's perfectly fine to just forget about Kullback-Leibler and focus on maximizing the expected log likelihood. Second, you may be wondering, was my expression for k hat from the previous slide missing a term? If I have a vector x and I want to calculate the sample average of this x based on some data, well, what would I do? I'd calculate 1 over n, the sum of xi. That gives me x bar. And if I'd like to calculate the sample variance matrix of this vector x, what would I do? Well, I could demean the x's, but another way to write the expression for the sample variance is as the average of the outer products of the x vectors minus the outer product of the averages. But this second term, the x bar prime term, it didn't actually appear in my expression for k hat on the previous slide. So you might be wondering, was that a mistake? Well, no, it wasn't actually, because if you take a close look at what that second term would be, you will discover that it would actually be the maximum likelihood estimation first order condition. And that sample average as a consequence would be exactly equal to 0, so it would drop out. If you find this confusing and you'd like to understand it in more detail, you can take a look at the video on the proof of the information matrix equality where I step through the details. Just a bit of terminology. This will be useful for the problem set and elsewhere. When I want to talk about the difference between the J-inverse matrix, which remember that was the asymptotic variance matrix if our model is right, versus the J-inverse times K times J-inverse, I need some terminology for that. So I will call J-hat inverse K hat times J-hat inverse the robust asymptotic variance matrix estimator, because this is going to be correct regardless of whether our model is correctly specified. Kind of in the same way that when we run a linear regression, we could use robust standard errors to allow for the possibility of heteroscedasticity.